Hi everyone. In this Connect with Networking video, we are going to continue our discussion of Chapter 4, the data link layer. In our last video, we were discussing error correction, and the simplest version of error correction is having the message resent. So anything that we might have missed, we just have repeated. But in some cases, that's not actually a practical way to solve the error. So sometimes what we pursue is forward error correction. And this is where we include some level of redundancy in the message that we're sending, so that when we do receive a message with errors, we can potentially correct those errors without retransmission. And we would use this technique in situations where retransmission is impossible, like for instance live broadcast, where you can't really pause the broadcast of the video or the audio, so you have to just keep moving. Maybe something where it's very costly or time-consuming, like communicating with satellites or communicating with distant spaceships, or other situations where retransmission is not practical. One technique for forward error correction is called a Hamming code. And this is where we apply parity bits to data bits in a particular sequence. By combining particular parity bits with particular data bits, we can determine not only that an error occurred, but where the error occurred and how to fix that error. So let's look at two different visualizations of a 7-bit Hamming code. And this is actually a 7-4 Hamming code where we send 7 bits in total. 4 of the bits are data and 3 of the bits are parity. Now keep in mind, this is not a particularly efficient way of sending information because almost half the bits that we're sending are parity bits or non-information bits. But if forward error correction is the name of the game, then this might be a good technique to pursue. In this particular diagram, parity bit 1 corresponds to data bit 3, 5, and 7, or the first data bit, the second data bit, and the fourth data bit. If any one of those bits doesn't match up, we would see that parity bit 1 and those 3 data bits don't have a common even number of ones or odd number of ones, depending on whether we're pursuing even or odd parity. Parity bit 2 is paired with D3, D6, and D7, or the first, third, and fourth data bits. And parity bit 4, the third parity bit, is paired with our second, third, and fourth data bits, D5, D6, and D7. By having all these different combinations, if a particular error occurs, we can determine not only that it happened, but where it happened. First, if we were trying to send a message and the data that we were trying to send was 1011, we would have to figure out what parity bits to send along with it. We're sending 7 bits. We're sending parity bit 1, parity bit 2, data 3, parity 4, data 5, data 6, data 7, in that order. We already know the data bits, and we're trying to figure out the parity bits. Parity bit 1 is associated with D3, D5, and D7. And those are 1, 0, and 1. So there are 2 1s and a single 0. That means that we don't need any more 1s. We have an even number of 1s. So our parity bit 1 would be a 0. If we want to figure out parity bit 2, we would have to look at D3, D6, and D7. You'll see that's 1, 1, and 1. And a 1 would make that an even number of 1s. If we want to figure out parity bit 4, that's paired with D5, D6, and D7, which is 0, 1, 1, which means we don't need an additional 1, so P4 would be set at 0. Parity bits are 0, 1, and 0 in this case. This diagram is the exact same technique, just a different visualization and slightly different symbology. We're still sending parity bit 1, parity bit 2, our third bit, which they're labeling D1, but it's really the third bit, P3, which is the fourth bit, D2, D3, and D4, which are the fifth, sixth, and seventh bits. It is the exact same sequence. It is the same parity bits and data bits with slightly different labeling. I like this example because I really like the diagram. The circles represent the parity bits and the data bits. You have to draw this picture exactly the way that it is represented on the screen, with 1 top circle and 2 bottom circles. If you draw this picture with the circles in different positions, this won't work. You also need to label them exactly correctly. P1 at the top, P2 in the bottom left, and P3 in the bottom right. And for the data bits, D1 at the 10 o'clock position, D2 at the 2 o'clock position, D3 at the 6 o'clock position, and D4 at the center. If you have an error in this particular example, what you'll see is that the parity bits don't work in a particular circle. So let's look at a specific possibility. What if you received the following information? 011, 0111. First, we'd have to know that the first and second bits are parity bits, the third is a data bit, the fourth bit is a parity bit, and the last three are data bits. And we'd have to know the parity bits that correspond with specific data bits, which we have in this chart and this diagram. If you look at the diagram, what you're hoping for is an even number of ones in each circle. But look at the green circle. You have a 0 and a 1 and a 1 and a 1, and that is an odd number of ones. So there's something wrong in the green circle. If we look at the blue circle, I have 4 ones, and that's an even number of ones. So the blue circle is okay. If I look at the red circle, I've got a 0 and 3 ones. So there's something wrong. There's an odd number of ones. If we look at the entire picture, there were issues with the green circle and the red circle, but not the blue circle, which means the error has to have occurred where red and green overlap, but don't overlap blue. And that would be D2. There's something wrong with D2. It's supposed to be a 0, but it was sent as a 1, and we could fix it and then have the correct data. We can do the same thing with any possible combination of zeros and ones. If only one circle has an error or one circle has an odd number of ones, the error is actually the parity bit. The parity bit was supposed to be a 0, but it was sent as a 1, or was supposed to be a 1, but it was sent as a 0. If there are two circles where there's an error, the error is the common space between those two circles, which doesn't intersect with the third circle. It's going to be D1 or D2 or D3. If all three circles have an error, then the error is in the center where all three circles have commonality, in this case D4. So by looking at these circles and looking for an odd number of ones, you can quickly determine whether an error has occurred and where that error has occurred and how to fix it. Do keep in mind that Hamming codes only detect single bit flips. If there was more than one error in these 7 bits, Hamming code would not allow us to determine it or fix it. So this is not foolproof, but it does a pretty good job of the task of fixing a single bit flip in a message. In practice, errors on wired connections are actually quite rare. We still have error detection and correction in place in case we don't receive something over the wire, but that doesn't happen very often, and it certainly doesn't happen at all, and it certainly is even more rare on fiber optic networks. When we're dealing with wireless, there's a lot more opportunity for interference, and so error detection and correction is even more important. And that's why some of the algorithms we use on wireless networks try to avoid errors more strictly in the first place, because once they occur, probably rebroadcast is your only safe bet for getting the proper information sent. Another responsibility of the data link layer is how we move the information from one place to another and how we delineate certain parts of the message. Some messages are sent using asynchronous transmissions, while others are sent using synchronous transmissions. And the different protocols vary in terms of how they delineate the beginning and the end of a message, how long a particular frame can be, and what the structure of that frame might look like. We'll take a look at a couple of specific examples just to give you an idea of how data link protocols have varied over time. One very simple algorithm or protocol for sending information is asynchronous serial transmission. This is an old transmission that was used way back with teletype, where you're broadcasting one character at a time, represented by either 7 or 8 bits. You would start a message by decreasing the voltage from positive to nothing. That small drop in voltage would indicate that a message is about to be sent. The next 7 or 8 bits would be your actual message, followed by a parity bit, very, very simple error detection, and then a stop bit that represents that that character has been sent, and now you're waiting for the next one. This is a super simple way of sending one character at a time, but it's not particularly efficient because we are actually using up a lot of bits for one small piece of information. Synchronous transmission is sending lots of data in a block called a frame, which would include additional addressing information and include some synchronization characters that let you know when the transmission has begun and when it ends. Some example protocols are SDLC, HDLC, Ethernet, which is commonly used today, and PPP. SDLC was developed by IBM, and it starts with a flag, which is always 0, 111, 111, 0. It's then followed by 8 bits which represent the address where the message is supposed to go, 8 bits of control, a variable length of data, followed by 32 bits of CRC, so our error detection, and then followed by the same flag of 0, 111, 111, 0. So when you see that pattern of a 0, 6 ones, and a 0, you know that a message is about to start. And then at the end of the message, you'll see the same pattern, 0, 111, 111, 0, which represents the message is actually finished. One issue with this protocol is that it's possible that inside your address, your control space, or your data, or your CRC, that you have a natural 0, 111, 111, 0 pattern. And that could confuse the recipient in terms of getting that pattern and thinking it's the end of the message, when in fact it's part of the message. So the way that IBM solved this problem was doing what's called bit stuffing. If you're not in the beginning flag or the ending flag, and your pattern is 0 and 5 ones in a row, you always add an additional 0 to interrupt that potentially natural pattern of a 0 and 6 ones in a row, followed by a 0, which could confuse the recipient. So there are some extra zeros that are sometimes inserted into an address or control space or data space or CRC space so that the data itself doesn't look like the beginning flag or ending flag. When the recipient receives a 0 and 5 ones in a row, they look to see if the 6th bit is a 0. And if it is, they remove it because they know that it's additional padding to make it look a little bit different than what it naturally looked like. If they see 6 ones in a row followed by a 0, they know that's the actual flag at the end of the day, and they know that they don't have to remove the 0, that the message is actually finished. This is a super clever way of having flags that are 100% unique, even in large data sets. However, it's still a complicated way of doing things, and so it is not a protocol that is used today. Instead, what we see commonly used is Ethernet. Ethernet starts with a preamble and some sort of delimiter that starts the message. It then has a destination address and a source address, so you know where the information is coming from and where it's going. It has 2 bytes that represent the type of information, and it has variable data size of anywhere from 46 bytes to 1500 bytes, followed by 32 bits or 4 bytes of CRC. The difference here is that this particular frame will tell you up front how large it is. So you don't have a flag at the beginning and a flag at the end. You have some information at the very beginning that tells you this particular frame is 1000 bytes of data. So you know exactly how long the frame is going to be, and you're not looking for some sort of ending flag. So you don't have to do any additional bit stuffing or pattern changing for the actual data itself. This is a fairly efficient way of doing things. If you constrain your data size to 46 bytes, your ratio is a little bit better than 1-to-1. But if you increase the size of your data up to 1500 bytes versus the 38 bytes of total overhead, you're getting a lot of data sent for very little overhead bytes. So a fairly efficient protocol for sending information. And efficiency is something that we want to pay attention to when we are using a data network. The simplest way of defining efficiency is the amount of information bits that we're sending versus the total number of bits, which would include both the information bits and the overhead bits. So if we're sending something like asynchronous, where we're sending a single character with a starting bit, a parity bit, and then an ending bit, the ratio is around 73%, which isn't bad, but we could probably do better. If you were sending a message using Ethernet and you were increasing the size of your message to 342 bytes or 722 bytes, you can see that the ratio is way better than 73% potentially And the fullest size Ethernet frame of 1500 versus 38 has a great ratio. So transmission efficiency is certainly an important characteristic of modern protocols. The issue with transmission efficiency is that it can be affected by how often we're seeing errors. If you're receiving a lot of errors, then sending particularly large frames could actually result in a slower network, because every time you receive a frame that's broken, you have to retransmit the frame. If the frames are big, they take a long time to receive and then notice that there's something wrong and then ask for retransmission. So you might actually ask for smaller frames. Again, there's a corresponding analogy to having a conversation with someone. If you have a conversation where you say a long sentence or paragraph to someone and they don't understand some part of it and you have to repeat the entire thing, that's not a particularly efficient way to have a conversation if you are regularly having those types of errors. So when you're in a situation where errors are occurring regularly, you might want to keep your conversation to smaller bite-sized chunks, one sentence at a time or even a phrase at a time. Think about, again, relaying your credit card information to someone on the phone. You often only relay 4 digits at a time, so that if there is an error, the error is small and the retransmission cost is fairly low. But in other cases where errors are unlikely, you can have much longer conversations without really risking the cost of retransmission. So the optimum frame size might vary depending upon how noisy your network is, how likely errors are, and how expensive retransmissions might be. Instead of looking just at efficiency, we might look at throughput. And one measure of throughput is transmission rate of information bits. And it takes more into account than just the ratio of data bits versus non-information bits plus data bits. And here's the equation we would use. It takes into account the information bits per character, the frame length in characters, the transmission rate in terms of characters per second, how many non-information characters we're sending in a frame, the likelihood that you're actually going to have an error and require retransmission, and how long it takes between frames. By considering all of these different factors, we can come up with the right size of a frame. And on modern networks, this might shift over time. Sometimes networks are experiencing a lot of noise, and so they'll shift to a smaller frame during that time period. Once the network starts to clean up and we're not seeing as many errors, we might start to increase the size of the frame again. So this can actually be a dynamic component to modern protocols. We shift the size of the frame as necessary. The implications of the data link layer for management is that really a lot of this has simplified over time. There are only a couple things we need to consider in the data link layer protocol. For wired networks, Ethernet is the only protocol worth considering for modern networks. Because we're only considering a few well-established protocols, managing networks has gotten a lot simpler. We don't need as many trained experts because they only need to know a specific protocol and set of technologies. And the equipment itself has dropped in cost quite a lot because the equipment doesn't need to be particularly sophisticated or able to handle multiple protocols. So the simplification of the data link layer over time has made network management that much easier. That's it for this chapter. Thanks so much for watching. See you next time.